Hello and welcome to this lecture on optimization. So in this lecture, we're going to look at the BFGS formula, which is a way of computing the descent direction. And I say continue to look at because this is a follow-on from chapter 4 of the type notes, which you can find on the website. So in particular, we're going to investigate the circumstances in which the BFGS method produces a positive definite approximation of the Hessian at each iteration. And having the positive definiteness property is key to generating a convergent iterative method. So just a quick reminder of what we're doing when we use the BFGS algorithm. Just to recall the Hessian matrix, we use the notation B, and this is the matrix of partial derivatives of the cost function evaluated at xk. Xk is the present iteration. And the rationale for doing the BFGS method is to avoid having to compute BK inverse at each iteration. You know, if you're doing the pure Newton method for computing the search direction, you would have to invert the Hessian at each iteration. And this is a costly operation, it's order n cubed. So the aim of BFGS is to avoid having to do this. And in this lecture, we don't quite get there. I don't quite get to telling you how to avoid computing BK inverse. But I build up the foundations. So the first step before you can compute BK inverse efficiently is to compute BK efficiently using the secant method. So that's what we do in particular in this lecture. And we characterize then the approximate Hessian as being positive definite. So yeah, following on from the type notes, to approximate the Hessian BK plus 1, we use this approximation, which is Taylor expansion. So yk is approximately equal to b at xk times sk, where in our notation, b at xk is bk plus 1. Sk is the difference between iterates, xk plus 1 and xk, and yk is the difference between gradients at xk plus 1 and xk. So in a shorthand notation, we've got yk equals bk plus 1 times sk. And the problem here is that this is n equations, but there are n times n unknowns because the unknowns are the entries of bk plus 1. And so this is an underdetermined problem. And BFGS addresses this by constructing an approximate solution for bk plus 1. And the idea is that we build our approximate solution out of two vector quantities, yk and bksk. And the approximate solution then is built out of an outer product of yk with itself and an outer product of bk times sk with itself. And also bk itself, because bk plus 1 is a correction to bk. So these are our three elements in our approximation of bk plus 1. And we form our approximation by taking a linear combination over the three elements involving alpha and beta. So again, yk times yk transpose is the outer product, and we can satisfy ourselves that this really is a matrix. It's an n by n matrix because it's an n by 1 vector, row vector, times, sorry, it's a column vector, of course, because it's got n rows and 1 column, times a 1 row n column. And this product then is an n by n matrix. And the components of the matrix or the entries are very, very straightforward. So yk outer product with yk, ijth component is just yki, ykj, the individual components of the vector making up the product. So this is our approach for estimating or constructing an approximation to bk plus 1, and we close the system of equations for alpha and beta by demanding that the approximation should satisfy the secant equation yk equals bk plus 1 sk. And we found already, recalling the lecture notes, that the general formula for bk plus 1 is given here in equation 1. So yeah, here in this lecture, we look in depth at the properties of the matrices bk and bk plus 1. In particular, we prove the following theorem. So provided B naught is positive definite and symmetric, and provided this important curvature condition is satisfied at each iteration k, then the BFGS method produces a symmetric positive definite approximation to the Hessian at each iteration. So the strategy here is a proof by induction on n, or I should say on k. So we start with the symmetric property. We're going to prove the symmetric property. So by the definition of bk plus 1, it's bk plus this linear combination. And for instance, yk transpose ij is yki ykj, and this is symmetric. So outer products are necessarily symmetric. So bk plus 1 is built out of bk plus symmetric matrices. So we do a proof by induction here. We start with a given B0, which is necessarily symmetric. So B1 will be B0 plus a symmetric matrix. So B1 is symmetric. And so on and so forth. B2 will be B1 plus a symmetric matrix. So B2 is symmetric. And so by a process of mathematical induction, bk plus 1 is symmetric for all k, provided B0 is symmetric. So we next look at the positive definite property. And again, it's a proof by induction. But we need to show that this inner product of xi with bk plus 1 times xi is greater than 0 for all xi non-zero. So we look at a direct computation. So we need to compute xi scalar product with bk plus 1 times xi. So by definition of bk plus 1, it's the scalar product of xi with bk times xi minus this combination here, plus a final combination which I've highlighted in yellow. And we're going to look at this last term first. So we focus in on the last term. So it's xi scalar product with the outer product of yk transpose xi, and then divided by the curvature, which is the scalar product of yk with sk. And you should be able to satisfy yourself that the numerator here is the scalar product of xi with the vector yk squared. So the numerator is positive because it's a square, and the denominator is positive by assumption. That's in the hypothesis in the theorem. So overall, the thing is positive. So yeah, you should check this algebra for the outer product. So going back to our expression for bk plus 1, the term highlighted in yellow is positive definite. So it remains to show that the first two terms are positive definite. And I just, for the work that we have to do, I call the first two terms delta. So we need to show that delta, which is the scalar product of xi with bk times xi, minus the scalar product of xi with bk, sk transpose bk xi, divided by the scalar product of sk with bk sk. We need to show that delta is positive. And we're doing a proof by induction. So we're going to assume that BK is positive definite. And we're going to show that it necessarily follows that BK plus 1 is positive definite also. And if we can establish this step, we're done. Because B0 is positive definite. So having established this step, B1 will be positive definite. And once B1 is positive definite, by the same argument, B2 will be positive definite, and so on and so forth for all K. So we make the inductive hypothesis that BK is symmetric positive definite. Okay, having made this hypothesis, then there's an eigenbasis of Rn called Ui. So BK is lambda I times Ui. The lambdas are the eigenvalues and the Ui's are the eigenvectors of BK. And all the lambdas are positive because it's a positive symmetric definite matrix. Sorry, symmetric positive definite matrix. And the eigenvectors span the space because it's symmetric. It's a symmetric matrix, so the eigenvalues span Rn. So any vector psi can be written as a linear combination of the eigenbasis, Ui. And these coordinates, the xi's, can be written as the inner product of xi with u times I. And I can do the same thing for sk. I can write it as a linear combination of the ui's, and the coordinates are sigma I. And it then follows that xi, scalar product with bk times xi, is the sum over I of lambda I xi I squared, just from these calculations here. And crucially, this is positive. So now that I've made the inductive hypothesis and I've made this decomposition into eigenvectors, I will sub the results back into my expression for delta. So delta is xi, scalar product with bk times xi, minus this complicated second term. And I sub in for xi, scalar product with bk times xi, highlighted in green. So that's the sum over I of lambda I xi I squared. And now I sub in for xi, using the decomposition in terms of eigenvectors, that xi is the sum over I of xi I ui. And this xi vector, I take the inner product of xi with bk, sk transpose bk, and xi again. All divided by the denominator, sk times bk, sk, and in terms of the decomposition into eigenvalues, this will be the sum over I of lambda I sigma I squared. And just noting in passing that this will be positive because the lambda i's are positive. So the next thing I do is I'm just going to rearrange the sums, which I had highlighted in yellow. So I take a sum over I and a sum over j outside, and so delta is the sum over I of lambda I xi I squared, minus the sum over I and the sum over j of xi I xi j, and then I'm left inside with an inner product of ui with bk, sk transpose bk, and uj, and then divided again by the denominator. So what I'm going to do next is, because I'm taking the scalar product of ui with bk, sk transpose bk, uj, I can have the bk act on the ui. But if I do that, I have to turn it into a bk transpose, which I've done here. But bk is symmetric, so it's the same thing as bk. So that's what I do here, a slight rearrangement. And furthermore, that has an advantage for us because I have BK acting on UI, so that's lambda I UI, and I also had BK acting on UJ, so that's lambda J UJ. So I plug those results in, and so delta is the sum over I of lambda I psi I squared. And what I was previously calling BK UI, that will now be lambda I UI. So that's a lambda I and a UI. And similarly, what I was previously calling BK UJ, that is now a lambda J UJ. And the lambdas come outside the sum. So I'm left inside to evaluate this one inner product. And to evaluate this inner product, I use this following key fact that I could work out from the fact that SK transpose is an outer product. So this particular inner product is just sigma I sigma j. And you might need to check the properties of outer products to verify that this is true. So now delta becomes the sum over I of lambda I psi I squared minus the double sum over I and j of psi I psi j lambda I lambda j. And the previous scalar product that I had is now just sigma I sigma j. And this is all divided by the denominator, lambda I sigma I squared. So this is my expression so far for delta. And I remember what I'm trying to do. I'm trying to show that delta is positive or zero. So what I'm going to do to establish this is to introduce some auxiliary vectors that will help us with our calculations, big X and big Y. So big X will have components xi, which will just be the square root of lambda I times xi I. And big Y will have components yi, and yi is the square root of lambda I sigma I. So I'm just rescaling xi I and sigma I by the square root of eigenvalues. And I can do this because the eigenvalues are positive. And when I do this, well, in the next line, I actually don't do anything apart from taking a common denominator with respect to the previous line, so that delta is the sum over I of lambda I psi I squared, which I had before, and now taking a common denominator, the sum over I of lambda I sigma I squared minus what I had before, the double sum, which I now separate out into a sum over i's and a sum over j's. So previously I had some i's, and I separate them out, and I had some j's, and I separate them out. So now delta can be rewritten in terms of big X and big Y, because lambda I psi I squared is xi squared, lambda I sigma I squared is yi squared, and then minus the sum over I of xi times yi, and then the sum over j of xj times yj, all divided by the sum over I of yi squared. Okay, so I noticed that this is the norm squared of x. So delta can be rewritten as the norm squared of x times the norm squared of y. And this xi yi is x dotted with y. So this is x dotted with y all squared, because there are two instances. All divided by the L2 norm of y squared. But I use the Cauchy-Schwarz inequality that x times y is greater than x dotted with y, even true for absolute values. So delta is greater than or equal to 0 by Cauchy-Schwarz. So going back this to the start, xi scalar product with bk plus 1 times xi is delta plus xi scalar product with yk all squared over the curvature yk scalar product with sk. The second term is positive provided the denominator, which is the curvature, is positive, and that's part of the hypothesis in the theorem. So overall, xi scalar product with bk plus 1 xi is positive. And so BK plus 1 is positive definite. So remember, going back to the inductive hypothesis, what we've shown is that if BK is positive definite, then BK plus 1 is positive definite. But again, by the assumption in the theorem, B0 is positive definite. So by mathematical induction, BK is positive definite for all K. And that completes the proof.